Welcome everybody. In this video we are using Euler's identity to understand what the geometrical meaning of complex multiplication is. So remember, we already defined the polar form of a complex number, r, which is the length of the arrow, times cosine phi plus I sine phi. And this was pretty useless because it's much more clumsy to write down than the Cartesian form. But now, since we have Euler's identity, we know that this expression in the brackets is exactly e to the phi I. And this here is what I call the useful polar form, because this is very good to actually do calculations with. In example 9.10, we arrived here. The useless polar form of this complex number, square root 2 plus square root 2 times I, would be this here. But now, magically, by Euler's identity, this clumsy expression transforms itself into e to the pi over 4 times I. And 2 is the length of the arrow, so the absolute value of the complex number. And now, the complex exponential function satisfies the same functional equation as the real exponential function. We just state that here without proof. You would have to manipulate the series using the so-called Cauchy product. We're not going to do that here, but we simply accept that e to the z times e to the w is the same as e to the z plus w for all complex numbers. Actually, we're going to prove a little bit later a special case here for purely imaginary complex numbers, and this is the only case that really interests us. But for now, we simply accept this as a fact. And using this and the useful polar form, we can now finally understand what complex multiplication really does. So we take two complex numbers, z and w. The length of z, or the absolute value, is r, and the absolute value of w is s. The angle of z is phi, the angle of w is theta. And now we have a look at the product, z times w. This is r times e to the phi I times s times e to the theta I. Now, complex multiplication is commutative, so I can switch these around. So here I end up with r times s, the product of the absolute values, and here the product of the e's, the powers of e. And now, using this functional equation, I know that this here is the same as e to the phi I plus theta I. I can pull the I out, and now I arrive at the polar form of the product. And this is very neat, because look at this. Here, the length of the product is simply the product of the absolute values of z and w. That is not so surprising. And now we see with one look that the angle or the argument of the complex product is simply the sum of the arguments of z and w. So to multiply complex numbers, you simply need to add their angles or arguments and multiply the length of the arrows. That's it. And this is proving very, very useful when dealing with geometry in the complex plane, for example. Or as we will see, for taking roots of complex numbers and so on. There are myriad applications of this fact. So here, didn't fit down there. You multiply the absolute values and you add the angles. That's it. That's the meaning of complex multiplication. So we look at a simple example. We're multiplying these two complex numbers. So, and as we see here, we need to multiply the absolute values. So square root of 2 times square root of 8. And then we simply need to add the angles. So here we have pi plus 3 pi over 2 times I. Now this here is the square root of 16, which is 4, and this here is 5 pi over 2i. And now to arrive at a unique polar form, we agreed that this angle here must be in the interval from 0 to 2 pi. So I have to subtract 2 pi and I end up with 4e to the pi over 2 times I. And since this is nothing but the polar form of I, length 1, angle pi over 2, we end up with 4i. Now a seemingly simple example, but it has profound meaning for the application of complex numbers in physics. For example, in electrical engineering or even quantum physics. We are looking at the map mu for multiplication, going from C to C, mapping a z to z times I. So we multiply with I. What does that do? Well, we assume that the polar form of z is r times e to the phi I. And as I already explained here, the polar form of I is simply 1 times e to the pi over 2 times I, because the angle is obviously 90 degrees or pi over 2, and the length of I is 1. So I could also omit the 1 here. And now I simply have to add the angles. So the new angle of the product is phi. The argument of our complex number z plus pi over 2. So the arrow of z gets rotated by 90 degrees counterclockwise. And this is the geometrical meaning of multiplying with I. So the map mu corresponds to rotating the arrows by 90 degrees counterclockwise. This should be a quarter circle, so this is the new arrow, and here we have a right angle. You can also see this by using the Cartesian form. So this is just as a side note, if you multiply this here by I, you end up with b times I squared, which is minus b, plus ai. So real and imaginary part get swapped around, and here you have a minus. And if this is AB, has the coordinates AB, then this arrow here with minus BA is exactly perpendicular to this one. But here in polar form, this is easier to understand. So we don't really need that. And now, as I said, for example, in electrical engineering, when you're dealing with alternating currents, and if you have a capacitor or an inductivity in your circuit, then the voltage and the current have a phase difference. For ideal inductivities or capacitors, it is 90 degrees. So this here would describe, for example, the voltage, and this here would be the current. And the best way to deal with this in an elegant fashion is to use complex numbers. So you're transforming your real voltage and current to the complex plane using these complex arrows, and then there's an easy relation between voltage and current, namely simply multiplying by I. And then you can work here and add different voltages or currents, and then you go back to the real projection and you have your actual voltage that you can measure in your circuit. So this is a very, very elegant way. If you ever should study electrical engineering, you will deal with complex numbers a lot more than you would actually think. So as a final example, if you remember exercise 9.2h, this was this tricky expression here, 1 plus I to the power of 10. Back then, in another video, we used the trick writing this 1 plus I squared to the power of 5, and then we could expand it, but this is much more easily done in polar form. Shout out to my friend Will at Math Solving Channel. Please check it out, very interesting math channel. He suggested back then that it would be much easier to use the polar form to do this exercise. Now this is easily transformed into polar form because the length of this arrow obviously is square root of 2 using Pythagorean's theorem. And the angle, of course, is 45 degrees or pi over 4. Or you could use the arctangent of 1. And now the 10th power of this expression is easily obtained, silently assuming that the same power rules for the exponential function hold as in the real numbers, but this is also true. So you take this to the 10th power, this is 2 to the power of 1/2 to the 10th, which is 2 to the 5. And this we already know, this is simply I itself, because this is e to the pi over 2i, by subtracting 2 pi here, which doesn't change, of course, the arrow. So you end up with 32i, which we already obtained back then, but when you don't see the trick how to do it, to do this in Cartesian form without the trick would be very, very expensive, because you need to expand using the binomial theorem and get very messy expressions, and here in polar form this is done very easily. So, to conclude, whenever you multiply complex numbers, especially when you take a complex number to any power, which is nothing but multiplying the number with itself, it is always an advantage to use the polar form. And in the next video, we're actually going to see how this helps us to find square roots, or actually any roots of any complex number. Thanks for watching, and hopefully I'll see you soon again on this channel.